gave way to the southerly fetch. They were still coming in from the northwest, but the trajectory origin had moved, but associated later on. And then a build-up then during this period. Okay, so that's carbon monoxide, basically dividing the period into four. Of more interest is, because carbon monoxide is really just a tracer, of more interest is the aerosol concentration. Now this is accumulation mode aerosol, greater than 200 nanometers, and all I've plotted here is the number, so this is just total number per cubic centimetre. And what we see, this is a log scale here, so you can see quite a variation here, factor of getting on to for 100 in the amount of aerosol. From relatively polluted conditions up here to extremely clean pollution-free air down here. Now, the question really that made us sit up when we came back after the end of the campaign was that during this period here and these two periods here, so leaving aside the monsoon, we had very similar meteorological conditions. You get basically sea breeze forced convection every day. So, copious biomass burning early on, giving you a lot of aerosol, gradually decaying during December to give us clean aerosol, clean conditions in February, and therefore the question was, can we detect an aerosol influence on convection? So the hypothesis, if you like, is that we have here a laboratory for deep convection, particularly on the Tiwi Islands, where you tend to get similar conditions. They're not identical, but similar from one day to the next. Can we use this natural laboratory to detect aerosol influence on convection? So that's what I'm going to start off. So this is the first set of, if you like, scientific results from this project. Well, the first and crudest thing, this is from Peter May in the Bureau of Meteorology. First thing you can do is just stratify the data. So what he's done is to look at various measures. Peter runs an advanced Doppler radar in Darwin, which gives you wonderful coverage, 3D coverage of this region where we were flying, so we could see exactly where all the convection was, and they're able to tell you whether the particles are rain, snow, and graupel, and so on, just in the same way as the Chiltern people can here. And he's just stratified the data to low aerosol on the left of each plot, high aerosol on the right, so rain area, area of high reflectivity, radar reflectivity, and then this is the total area where there's any reflectivity, radar reflectivity, and finally the height, maximum height of the radar echoes, if you like. Not the total radar echoes, they're generally always at the tropopause, so he's chosen 40 dBz, which is basically intense echoes. And there's a hint here that, yeah, well, maybe there's something to investigate here. Okay, so that in itself, as you can see, the error bars overlap, so you wouldn't allow your student to publish that, but it gives you an idea that there might be something worth looking at. Okay, now, this work has been done mainly by Paul Connolly and Min Zhu at Manchester. It should say Connolly there. And they've taken a number of models, actually, to investigate this. This is a prediction from the WRF model. The WRF model is a three-dimensional simulation of the Tiwi Islands. So they've chosen a domain over the Tiwis, 1 kilometre resolution. It's convection permitting, half a kilometre in altitude. And basically they've run this thing with identical meteorology and modified the amount of cloud condensation nuclei getting into the bottom of the cloud. So they just initialize the CCN differently. And what you find basically is a kind of Goldilocks effect. If you have insufficient aerosol, if you have very clean conditions, then what happens is there's not many condensation nuclei for the droplets to form on as the air ascends. So you get a few large droplets, relatively few. So rainfall forms quite quickly, so you get warm rain. As you increase the number of cloud condensation nuclei, the droplets are not so big, so they're able to go higher. And the key to this game is to reach the freezing level. Once you've got this stuff to the freezing level, which is about minus 37 degrees, which is, in this case, somewhere between 5 and 9 kilometers, depending on the time, When that happens, you get freezing, a sudden burst of latent heat, and basically there's a reinvigoration of the storm and re-entrainment of material into the storm as well. So forming the anvil. And you can see if you've got too much stuff coming in here, then basically you fall ice too low down in the cloud. And that suppresses this material from getting to the normal homogeneous freezing level. So that's what the model thinks should happen. And what we've been trying to do is to see whether the data give us any clue as to whether that hypothesis is right or not. These models have got enormous numbers of assumptions in them, not least of which has to do with the reason for this. But anyway, I tend to be skeptical of models. So there we are. Paul's found this is the optimum 300. Keep your eye on the 300 now, because the story gets good now. Right. So again, somewhat frighteningly, but Paul has looked at this data in lots of different ways, and what I'm going to present to you is a nonlinear regression that he's done. So nonlinear regression of what? Well, we have all these days when we have these hector storms. 40 or so days, and then we have CCN values for each of them, because we can take the aerosol measurements, the composition and the number, and we can generate, using a chemical model that we have in Manchester, we can generate a CCN number for those conditions. We didn't measure CCN directly, unfortunately. And then we can sort of play games and say, well, what kind of influences can we detect from these data? Now, first of all, wind speed and direction are important. This is just for Hector over the Teely Islands. The wind doesn't always come from the same direction. You can see this is 40 degrees and 90 degrees, and this is the fraction of the domain. So basically this is the size of the anvil, if you like. That's what this technical term means. So the size of the anvil. And the anvil gets bigger as the wind goes more to the east-west. That's just because the islands are longer. What tends to happen with these islands, if you've got too strong wind, and you can see it quite clearly here, if the wind is too strong, it blows the storm off the island, so the storm doesn't get a chance to develop. So the behaviour is exactly what you'd expect from a model study. There's been lots of model studies of this. Relative humidity in the boundary layer, well, not surprisingly, the more fuel you put into the storm, the more energetic it is, so that's not a big surprise, but the data does show you that. And I think that's what, he's gone for this one first. One of the confounding factors is that you can get a lot of cirrus blown over from storms over the mainland, and this, of course, has the effect of shutting off solar radiation, which hooks the boundary layer over the storm, over the islands, and is basically the energy source for these storms. So that can be a suppressant, and you can see there's a correlation there. So you take all of these factors into account, there's the boundary layer humidity, and you find that the variation with cloud condensation nuclei is surprisingly, to my mind, consistent with what these model results were predicting. So we've got independent evidence, there's no model gone into this at all. This is just looking at the data. So there's the warm rain effect there, and the other rhyming effect on the right-hand side here, the ice phase suppressing the size of the storm for high CCN numbers. So it seems as though we managed to show, and there's Goldilocks in the middle there, dynamical enhancement he calls it, but it's basically because more water manages to get to this homogeneous freezing level. Okay, so the first result is that we seem to have managed to get enough evidence together to make a reasonable argument that this non-linear variation with CCN is real and not just an artifact of the way the ice processes in the models have been parameterized. Okay, so that's the first set of results. Now I'm going to turn to the question of transport and what is the relative balance between longer range transport and local transport on the TTL over this region of Northern Australia. And I'm going to use both aircraft and ozone sondes to do this. I'm going to start off with the ozone sonde profile. If I were to do this experiment again, I would launch 3 times as many ozone sondes. We got a huge amount of science from these rather low-key